So I'm just going to repeat what I said just so everybody can have it. All right, so final exam, Tuesday, July 23rd, 2:30 p.m. And I got to say this because some of you guys be trying to. So this is Eastern time, and I know some of you guys might be in different time zones, so I got called out on that. I'm assuming that everybody's in Florida, but this is Eastern time, so make sure that you're using Eastern time as the standard. There's going to be about 20 questions, all the chapters that we covered in class. You'll find it in the submissions, under the submissions tab, subsection quizzes. You can have a 3-inch by 5-inch note card. You can fill it out back and front. Your cameras have to be on, no hats, and your face needs to be visible. Okay, and I think that's where I left off. So now, are there any more questions that you guys have? Anything that I missed? Okay. All right, so let's go ahead and get started. Not sure. I'm on my iPad right now, so I'm pretty sure everything should come out okay. All right, so as I said before, these are all my handwritten notes over the years. And so hopefully, we're gonna see each one of the problems. If not, we will have to kind of improvise here. And I'll probably have to grab a few and screenshot them. Let me read the first one. You guys might need to kind of expedite this since we have so many questions. You guys may need to look on the website here. Sorry. I thought I had all this stuff pulled up. Give me 1 second here, class. I want to split my screen. Let's go into that class. Because we need to have some reference for the recording. So I'm in the class. I'm going to go to course content. I'm going to go to the practice final review. And these are the problems. All right, the first one I didn't write down because that's more of something that you should kind of have memorized and you should recite to yourself. It basically says that the sum of all forces in a certain direction, I'll write it over here. So number one, sum of all forces in a specific direction, let's just say X, is equal to mass times the acceleration in that same direction. So that's Newton's second law. That one we use quite a bit. Okay, number two. Number two says you're driving home on a weekend from school at 55 miles an hour. You're going to go 110 miles. And I'll use my highlighter on the left side over here so you can kind of follow me. Try and get this toolbox out the way. There we go. It then starts to snow and you slow down to 35 miles an hour. You arrive home after driving 4 hours and 15 minutes. How far is your hometown from school? All right, so let's see what we have here. So this entire stretch here is that distance from school to home. It told us that our first distance was 110 miles. You're gonna have to pardon me one more time because I need to split the screen. I shouldn't have. Sorry. Should have left that as a side view. Okay, so it says that you drove 110 miles for 55 miles an hour. And so that's the stretch on the left. And it says also that it takes, do this one more time. All right. Last take on this. And then it says it takes you, it then starts to snow and you slow down to 35 miles an hour. You arrive home after driving 4 hours and 15 minutes. How far is your hometown from the school? All right, so back on to the piece on the right side over here. We know this entire distance, right? Well, we're gonna have to find this entire distance. Our goal is to figure out the total, our X is the total distance that we drive. We know this first part, right? So we need to find this second stretch over here given this information. So if the total time that they gave us was 4 hours and 15 minutes, that equates out to 4.25 hours, so 4.25 hours. Don't get caught up in this. Don't think it's 4.15, right? So it's 4.25 hours. And then we're going to use this formula here for distance on both sides of this distance piece. All right. So in the first area, it says that we went 110 miles and we went at a rate of 55 miles an hour. If I know that, then that tells me that my total time on this end is 2 hours, which means by default, because I know the total time is 4 hours, 4.25 hours, that means there has to be 2.25 hours remaining, right? So this leads to this. Therefore, I should be able to figure out what my rate of time was in this general stretch, or the distance given that stretch. So it told us that my rate of time when it starts to snow, this is when it starts to snow where the little bar is. When it starts to snow, I slow down to 35 miles per hour. So therefore, given these two pieces, the rate and the time, I should be able to figure out the distance. And this distance right here, the 78.75, is the distance in this second stretch. Okay. So if the distance in that second stretch, how we get that is we take the rate at 35 miles per hour, multiply by the time. Remember, we found that sort of by process of elimination. So this is the distance in the second stretch. We add that to what we knew to be the distance in the first stretch, and the total distance that we drive is about 188 miles. Okay. Any questions on that? Okay. So best answer there would probably be B. So you got to choose the answer that's closest to it. So you got to think think of rounding up in that case, right? Using two significant figures. All right, number 3. I kind of have a feeling I'm not going to be able to get to all 50 of them, so I'll probably ask you guys to give me some suggestions here in which you might be struggling on. All right, number 3. Number 3 I kind of have already written down, so I won't use that side piece. So it says, how much further in feet would a drunk driver driver's car, would a drunk driver's car travel before he or she hits the brakes than a sober driver? Both are initially traveling at 55 miles an hour, and both have the same deceleration. So once I hit the brakes, I'm going to decelerate. The sober driver takes 0.33 seconds, while the drunk driver takes a full second to hit the brakes. I have a conversion factor here that says 1 meter is equal to 3.3 feet, just in case I need to convert. And I believe I did, because that was one of the selections. It wasn't one of the selections, but it's just something that I do just in general. Okay. So for number 3, the first thing I'm going to do is I'm going to figure out what my distance, what this driver's distance was. So we're looking at the sober driver over here on the left side, and we're going to figure out his or her distance. If they're traveling at 55 miles per hour, or actually 29.59 meters per second, and I go and it takes me 0.33 seconds. In other words, from the time that I see this red light, right? I see the red light. Here's my car. I'm going to travel a certain distance before I hit the brakes. Right? And so that's what we want to figure out. And that distance turned out to be 8.1 meters. If I do the same thing for the drunk driver, so I'm over here for the drunk driver, it's going to take him or her a full second more to stop the car. Right? That person is going to travel this distance over here. Remember, they're both initially traveling at the same speed, about 25 meters per second, which is 55 miles an hour. And so this person here on the right is going to travel that much further before he or she hits the brakes. So instead of that initial distance that you see on the left in the picture, that person's going to travel even further. Right? So more likely to hit, not be able to stop and hit, more likely to hit somebody over here. This person right here is less likely to hit somebody if there's an object in the way. And so the drunk driver is going to travel 54 feet, which was equivalent. It should be equivalent. I don't know why I didn't convert that. No. Sorry. The drunk driver is going to travel 24.6 meters, while the sober driver goes 8.1 meters. The difference is going to be 16.5 meters, or about 54 feet. Okay. So the drunk driver travels 54 more feet than the sober driver. Then I just did it another way down here in the second area. I just looked at the distance that each one of them traveled, and then took the difference between those two. Okay, so you get roughly about the same thing, roughly about 50 feet. Any questions on those first three problems. Okay. Any requests? We can look at any of the problems. I'm pretty sure I've done all 50 problems in here. All right, I'll just keep going. Number 8, very good. All right, so number 8. I'll go slowly through this just in case you guys want to look at my notes in the recording. All right, so we're here at number 8. So number 8 says, an airplane needs to reach a forward velocity of 203 kilometers per hour to take off. So that would be the first thing I would think of. That is a little bit of a red herring there. I would probably think to myself that I need to convert that into meters per second. So that would be the first thing that would furrow my brow if I were looking at this. All right, so we're going to try and go, we're going to try and take off, but we need to reach 203 kilometers per hour to take off. And then we're going to be on a runway of 2,000 meters. We want to know what is the minimum uniform acceleration necessary for the plane to take flight if it starts from rest. Okay, so essentially we're trying to figure out the acceleration. And the acceleration we're going to assume is constant here because it says that it's uniform. And that's an indication or a key to let you know that you're going to probably use some kinematic equations. So if you see uniform acceleration, constant acceleration, constant velocities, those are all keys to let you know that there's a possibility. I don't want to say it's 100%. There's a possibility that you're going to use kinematic equations. So with that, what I would do is I would write down these pieces. And I may have to do this one. Oh, I made an error when I plugged in, but I corrected it when I went down below, and I'll correct it on the fly right now. All right, so we know that V sub F is going to be our 56.39 meters per second. And so in that chart, that should be 56.39. So there's my final velocity or future velocity. I'm starting from rest. So therefore, my V naught, my initial velocity is 0. My displacement, I'm going to go about 2,000 meters. Again, keep everything in SI units. If they gave you something that was in kilometers, let's just say 2 kilometers, you're going to want to convert. So just kind of be on the lookout for those things. We're trying to figure out the acceleration, and we weren't given a time. Okay. And so you'll know which one of the equations to use based on what you're trying to find. You can see in this row here that we have only one unknown, and we have the unknown that we're looking for. So in this third row here, we have that one unknown, but that's not what was asked for in this case. it might be helpful for some other problems, right? And I could easily switch it up on you and say, we'll find t. Make sure you can solve for t given variables such as this. Okay, is that clear? That helpful? And
Yeah, thank you.
I'm not sure if I need to write everything down verbatim as we go through here, but I think it'll be a little bit more rapid if we do it this way. Okay, number 9. So number 9, we have a ball that's thrown straight up in the air with a speed of 30 meters per second. We're going to have air resistance that is negligible. And we're going to try and figure out how long it takes the ball to reach its maximum height. We're going to try and figure out what the maximum height is, and we're going to try and figure out what its speed is after about 4.2 seconds. Okay, so what we're given that we're only going in the y direction. So the ball is going to do something like this on the upswing and then straight down on the downswing. So there is no motion as such, right? So there is no component in the x and the y direction. There's only components in the y direction. And so we're given that our initial velocity, and just to be even more specific here, we can say the initial velocity in the y direction is 30 meters per second. And you can see that right here. We don't know the displacement. I just replaced that x with y. And because this thing is dependent on gravity, this is our acceleration in the y direction, otherwise known as g. Okay. And I'm sure everybody knows what that number is by now. And then remember, you have to define which way positive or negative is. So if you define down as negative, that means because acceleration due to gravity is in a downward direction, you're going to make that sign negative as well. So the signs on these things are going to be really, really important. Just like the initial velocity here is going to be positive for us. So my suggestion is just to make fewer variables for you to have to keep track of, stick to a standard format. Up is positive, y is negative. If you're going left or right, let x be positive. Just keep it standard. Okay, unless you like to the right being negative. I don't know. Okay, so let's see. Let's see if we can figure out part A. How long does it take the ball to reach maximum height? Well, let's figure out why I put that very first column as 0. Our first column is 0. This is going to be that future velocity when the ball reaches a max height. So right here, it's at max height. We know that the velocity in the y direction is equal to 0. So this is Vy equal to 0. This is at max height. Okay, and so that's why I set that piece, this piece right here, equal to 0. And then at this point now, all you're left to do is to figure out which equation you want to use. And I went on and solved using that second equation. Okay. So make sure you're clear on that. The reason why most people get this wrong is because they either pick the direction for downward incorrect. They don't account for downward being negative, and because we're going to need to look at it in terms of displacement later on as well. So we'll see some problems. I think in just a second we'll see a problem where we're going to start here. Let's move it out a little bit. We'll start here, and the object is going to move down here. Well, if you say that downward is negative, that means that this object is going to have a negative displacement. And so you're going to need to plug in some negative value there for the displacement in the y direction. Okay. All right. And then same thing for the max height. All you're trying to do is to figure out what this y value is. At this point, it's at part B, you've already figured out what t is, right? T turned out to be 3.1 seconds. So you would just simply plug in there. And then you have some options in terms of which variable or which equation you want to use. Okay. So I just kind of just did it over again, plugging in 3.1 for t, and now I'm solving for y. And y should better be a positive number here because we had a upward displacement and we said upwards was positive. If I didn't get a positive displacement, then that means I probably did something wrong, or I decided that upwards was negative. Okay, so if you chose upwards as negative, you're fine. Okay, so just be careful on that. Then part C asks for what is the speed after 4.2 seconds. So now we kind of reset the chart here because we can't use, in this case, that very first column, we can't use 0 here. This is what we're trying to figure out. Remember, this is our future velocity. Future or final velocity. Right? I like to think of future because that's not the final velocity. It's some velocity that we're going to have in the future. The initial velocity still stays. Okay. The displacement in the y direction, well, we don't know where it's going to be given after 4.2 seconds. If our picture goes up and then comes down, we don't know if we're going to be we don't know if we're going to be up here, down here. We don't know where we're going to be. I guess we can kind of make some assumptions that because we're the max is at 3.1 seconds. After 4.2 seconds, we should be in this stretch coming back down. Okay, and so in this case here, we're looking for that velocity. We're given v naught. I underlined y as if we were looking for that, but we weren't looking for that. We were looking for this future velocity. And so at this point here, we should determine which equation we want to use. I use the second equation because it involved my v future and it only had one unknown. Okay. And it looks like all the other equations didn't involve v future or had one unknown, such that we didn't need that unknown. Okay, give me 1 second here, class. Sorry. Okay, so here again, we can see the direction of the velocity vector. It is negative, which means that if I'm on this track here, my velocity should be pointing downward. Right? That's why I say it's probably easiest just to keep everything kind of, if you will, standard. Up is positive, down is negative. Makes things a lot easier to keep track of. Okay, any other requests here? All right, I'll just kind of
You
keep
do
going.
number 12.
Number 12. Okay, so let's put it on the screen. Okay, so we're gonna have 3 ropes, and they're gonna be tied to a knot, and we're gonna have a person, student. The one student is gonna pull rope A with 1 pound of force. Instead of newtons, they're just using pounds. Another's gonna pull rope B with 7 pounds of force, and another one is gonna pull rope C to balance the first 2 pulls out. We're gonna try and give the direction by specifying the angle of the pull with the rope. So let's see what we have over here. Okay, so now I think I might want to just draw this one over again. I'm gonna let me add a page here, and kind of try and work this one from scratch somewhat. Let me copy this. All right. So the thing about this picture is the this rope C is not really drawn to scale, nor is it drawn exactly where it should be. So what we're going to need to do is we're going to need to figure out the components of each one of these ropes that are given, and then understand that the system is in equilibrium, which means that the sum of the forces in each one of the directions are gonna, if you will, knock each other out. So let's do it first here before. So rope A we'll write as a vector. It can be thought of as so many units in the I direction plus so many units in the J or J hat direction, or Y, if you will. We can see clearly that rope A has no components in the Y direction, only in the X direction or I hat direction. And it was stated that it had a force of 1 pound. Right, so we can just simply write that as 1 I hat. And 0 J hat. While B has both X and Y direction. If you look at it from this standpoint here, you can kind of see, if we go to the left, there's the X component of B. And as we go up, there's the Y component. All right, so there's the Y component right in there. And those two add up to give me that piece right there. And so the question is, well, how do I figure out each one of these pieces? Well, we have a formula that said that we take the magnitude times the cosine of the angle that's given, in this case, 120 degrees, in the I hat direction, plus, again, the magnitude. I'm going to skip a little bit here. Well, I'll just write it because I'm going to have to write it over. And then sine of 120 degrees in the j hat direction. Or the magnitude, remember, is given as that 7 pounds of force. So I'll have 7 cosine of 120 degrees in the I hat direction. Same thing with sine, but in the j hat direction. And so if I do the math on this, see if I can cheat a little bit here. What happened to that problem? Oh, here we go. We should get negative 3.5 and positive 6.1. So negative 3.5 in the I hat direction and positive 6.1 in the j hat direction. Okay. And so remember, what's supposed to happen is A and B are supposed to be able to counteract C. In other words, A plus B has to equal C in order for this thing not to move. An easier way of thinking about this is when I add up all the components in the I hat direction, they have to add up to 0. And same thing with the j hat components, right? So let's see what I get. So how about I do this? So here's my B. I'm looking at this component and this component. I'm going to find out what C is somewhat. If I add 1 and a negative 3.5, I'll get negative 2.5. But remember, C has to counter that. So A plus B, I kind of wrote it. Wrote this just a little bit. This one's a little bit off here. So let me do this. So this is negative 2.5 when I add these two together. And so C has to be positive 2.5. Okay. I'm going to erase this up here. This was an error on my part. So A plus B plus C, they have to add up to 0. In other words, A plus B has to equal negative C. Okay. All right. And so one more time, if I look at these two components, so 0 plus 6.1, we get 6.1. Therefore, C has to equal negative 6.1 in the j hat direction. So when I add up all these components, I get 0. Same thing over here, I get 0. This just basically tells me that I'm in equilibrium. Okay. We should see an answer that looks like that for C. 2.5 I hat minus 6.1 in the j hat direction. And so let's answer the question here. It says give the direction by specifying the angle of the pull with the so relative to x. So any questions so far? I'm about not halfway done with this problem. All right. So let's erase all of this. And we're going to redraw this piece. So here's A. We don't need to do it perfectly. Here's B. Now, theoretically, since A is 7 times shorter, if you want to, just to kind of get a good gauge, you might want to just kind of draw it a little bit shorter, the A vector, but to make it fit, we'll be fine. And then let's put coordinate axis on here as well. Get some reference. This angle right here was 120 degrees. That was given. And now C, we just found to be 2.5 negative 6.1. So 2.5 negative 6.1 lands me 2.5 units here, and then negative 6.1. So terminal point is here. And so really, my vector looks like that. So here's C. And now if I'm trying to figure out the angle relative to A, I'm trying to figure out that angle right there. I'll probably just draw another triangle to let me see what's going on there. I have, let's see, this length here, which is that C. I have this piece right here, which I know is 1. I have this length right here, which I don't know offhand. I do know that. And this side over here is not 1. So should be drawing this triangle. So let me erase that. I'm just looking for the eraser. There we go. All right, so this length right here was 2.5. And it's really not, it's not drawn to scale. Let's put that as a disclaimer because this piece, right? Because A is only 1 unit long, but that won't hurt us. So we'll have 2.5 here. We'll have negative 6 right here, negative 6.1. We're looking for that angle, maybe call it theta. We take the tangent inverse of y over x of negative 6.1 over 2.5. I'm going to do it on my calculator here real quick. Second function tangent, negative 6.1 divided by 2.5. I get 1. Let's check my So always check your mode on your calculator before you do these. Mine was already changed to degrees. So I get 67.7 degrees. So theta is equal to this angle right here is equal to about 67.7 degrees. So roughly about 68 degrees. Okay. Always be mindful and know that tangent inverse is only going to give you values between negative 90 and 90. So if you had a vector over here, let's just say, you would have to improvise. If that angle right there were that 68 degrees, and I ask you relative to A, you'd have to rotate another 180 degrees to capture that. So just be mindful. That's why I always tell people to draw their vectors. Draw where your vectors are and try and draw them to scale if possible. But in this case, it's not going to hurt us. All right. Let's look at number 13. Okay. So 13, we have a vector, call it A, with a magnitude of 6 meters, and it points 30 degrees north of east. We have another vector B with a magnitude of 4, and it points 30 degrees west of south. And we're going to try and find out the resultant vector. Okay. So in this case, I think I'm going to copy it over again so we have some reference again. Right there. There we go. All right. So here's A, has a magnitude of 6, and it points 30 degrees north of east. So how do we get there? So what you're going to do is you're going to point towards the east. You're going to read this backwards, if you will. It's the easiest way I can teach you to remember this. You read this backwards, you read it in this direction, you point to the east, and then you're going to rotate towards the north. So you rotate in this direction towards north over here. So many degrees. Doesn't have to be perfect. So there's your vector A. Okay. And you would do the same thing for the other vector. The other vector says 30 degrees west of south. So point your vector towards the south as such, and rotate towards the west as such. And that interior angle there, hopefully you see that, this angle right in here is that 30 degrees that you just rotated through. So we're looking at those two. We're looking at those two vectors. And so let's see what we're asked to do. We're going to try and find the resultant vector A plus B. Well, we can't add vectors as it stands just yet. Now we can kind of get an idea if we've drawn this somewhat precisely. Let's see if I can pull up a ruler here real quick. So if you were to look at this maybe from a more precise standpoint, you guys probably did this in the lab. You might want to put that at 30 degrees. That's roughly about 30 degrees. So we'll roll with that. And this angle relative to 90 degrees, right here is 90. If I rotate in this direction, I get about 30 degrees. So that's decent as at least in an approximation. So if I wanted to figure out the resultant vector, I could, and this is why I like using this, because I can be a little bit more nimble here and show you. So I would take that one vector, which we call B, and put the tip of it or the tail of it on the tip of vector A, right? So that's that tip to tail method. You can kind of see it right here. I drew it right there, right? So just take this vector over here. You want to try and keep it drawn on the scale. I think in my notes, I tried to keep it the same distance, same length. Draw it here. And the resultant vector is going to be that vector from the tail of the first to the tip of the last. Okay. So there is my resultant vector. I called that R. At least we have some idea if we're in the ballpark. That's the tip to tail method. And so let's see, I might be able to reason out if any of these are not good choices. So I got to know directional headings, obviously. And so relative, let's see, the first one says, just a real quick drawing, I'm going to point to the east and then rotate. So I point to the east and rotate 8.3 degrees to the south. So it may look like that bad x-axis drawing, but I think you get the point here. So that may be reasonable to compare to what you see down here. Okay. Let's see about some of these other ones. This one, point to the south and rotate to the east 8.3 degrees. Well, that would mean if I just took the same vector here, that would mean if I started south and rotated to the east, that would be more in terms of what that vector will look like. And if I've drawn these to scale, I could probably reason out that anything that is east of south can be eliminated. And yes, there will be multiple choice on this test. So I can kind of eliminate those two. Now, the more precise answer is to decompose the vectors as I've done here and then add them up. So I'm not going to take you through again how to decompose a vector. We've done it in the previous. So A gets decomposed to be 6 times cosine 30 degrees I hat, and then 6 sine 30 degrees j hat. B, same thing except with 4 and cosine of 240 degrees. So the resultant vector is a vector of 3.2 in the I hat direction and negative 0.5 in the j hat direction. And so it looks something like this. And if I take the tangent inverse of the y component, which was negative 0.5, and divide that by the x component, which was, I think I did another one in my notes, so let's just do it right here. So tangent inverse of negative 0.5 divided by 3.2. Again, always checking my mode. The tangent inverse of negative 0.5 divided by 3.2. And I get about 9 degrees. Okay. And so that rotation or that angle that you're finding is this angle right in here. Because remember, you're looking at this triangle, with this triangle right in for this blue vector, you're looking at this triangle right in here, right there. And take the components of that for that resultant vector. Okay. Always use right triangles, and almost always you're going to go back to the x-axis. So don't use this. It's probably not going to give you anything worthwhile looking at. I mean, it has the same same components, but usually we look at the angle. We're trying to find that reference angle. Sorry. We're typically trying to find this angle right here. Okay. Okay, we'll take a break in just a second. All right, number 14. So number 14 is a typo. I've never gotten through that one just yet. So we'll just work with what we have here. Never corrected it. So here's one where I was talking about where it's important to know the direction in which these things are moving. So we know we're probably going to use our kinematic equations. Let's read the problem here. We have this figure. We have a rock that's going to be shot up from the edge of the vertical cliff, and it leaves the edge of the cliff with an initial velocity of 15 meters per second. Right. And it's going to be directed at 25 degrees from the vertical and experiences no appreciable air resistance. So we neglect air resistance. How high is the cliff? So with this one, what's a little bit tricky about this is that the author states here, let's see, the author states right here that it's 25 degrees from the vertical. And typically, we look at things relative to the horizontal, right? So if this is my XY axis and I say we're going to draw a vector, we typically say relative to the horizontal, let's just say 30 degrees, right? But in this case, he's saying relative to the vertical. That was that same picture. That would be the angle. Specifically, he's saying, in this case, relative to the vertical being that 25-degree angle, which makes relative to the horizontal that 65-degree angle. And this is the angle that we typically use when we start to decompose a vector. So over here on the right, I've decomposed the vector. You should know how fast it's going in the x direction and how fast it's going in the y direction. So this vector right here, that v naught, probably only helps us, I'd say, 10% of what we're looking for. The main driver of this is the decomposition piece. We're only going to use that number 15 to figure out, what the magnitude of this vector is. Once we figure out the magnitude of the vector, we need to know what that vector is doing in the x direction and what it's doing in the y direction. So that's what's going to be really important for us. Okay. All right. So, let's see if I finish this problem. I think I finished this problem. Let me copy this. Let's do it this way. I'm looking for a kinematic chart that I can copy over here, class. I think I'm just going to use this one and just look a little messy because I don't think I'm be able to erase. All right, so let's see what I have. Yeah. Let's take a break so I can rewrite this. So let's take a 15-minute break. So let's come back at 3:50. I don't want to sit here and recreate this chart for us. So 3:50 p.m., let's come back. split my screen just in case we need to. No, we'll stay right here. All right, so this is where we left off. Sorry. You guys still hear me? All right, thanks. Screen just blanked out. All right, let's start again. Share my screen. There we go. Yeah. All right. So we were talking about this object that was thrown off the edge of a cliff, and it's going to leave the cliff with initial velocity of 15 meters per second, directed 25 degrees from the vertical. And that was the little tricky part to this. And I showed you up here how to decompose that vector as such. Over here, I gave you just a quick example of another way of describing it. All right. And so this is going to imply that we use our kinematic equations for a free fall object. So let's go through this left to right so we understand how I got all these numbers. For projectile motion, any object that's going to travel is going to travel in, you're going to assume it's going to travel in this parabolic shape. Given any point in time, its horizontal component of velocity is going to stay the same. So we decompose this vector here to look like, instead of that, we made it look like, we'll only look at the x direction first. We made it look like this, right? Which was the initial velocity in the x direction here, a 6.3 meters per second. And we also made it look like this, which was the 13.6 meters per second. But at any point in time, as I said, this component is going to be the same. Okay. So let's get rid of that mess. So I'm only focused in on that x component. And so over here, it will be at 6.3. If our vector is here, it's going to be moving to the right at 6.3 meters per second. 6.3 meters per second. All the way up until an instantaneous second before it hits the ground. Right? So we never measure the velocity when it hits the ground. All bets are off then. Right? So that's how I came up with this final velocity or future velocity. At any point in time, we know what's going to happen. So we're going to try and figure out when that object is over here. Right? We always calculated instantaneous second before it hits the ground. I got to say that because otherwise, if you say everything goes to zero, you're technically right, but you will not get any mathematical information. The third row or third column corresponds to our horizontal displacement. If we say that to the right is positive, then we're talking positive 34 meters. And then, as we said before, our velocity in the x direction stays constant, which means that our acceleration is 0. So this comes as a byproduct of those two. The time wasn't given, so we now look at the information that pertains to motion in the y direction. All this pertains to motion in the y direction. Our final velocity in the y direction over here, well, we know on the left side, when we start off in the y direction, it goes up. It goes up. Over here, there's no velocity in the y direction. Over here, it's a little bit less. But after it reaches that apex, remember this is when that Vy is equal to 0. After it reaches that apex, now that velocity vector points down and further down and further down. You can see I've tried to draw those three vectors so that the lengths are extended. Okay. And so we won't know what its final velocity is. It wasn't given, but we can figure it out once we fill in some of the blanks. Our goal is to figure out what that y length is. In other words, how far we have traveled in our displacement. So we're trying to figure out this distance right here, which is that height. Okay. So what is our displacement? That's what this piece corresponds to, the displacement in the y. Not the total distance that it traveled, not that, but the displacement. And our displacement is calculated by where you started versus where you finished. Right? That's our displacement. All right. And so in this case, we need to figure out which equation we want to use in order to calculate y. If you look at the right side of this kinematic chart over here, it looks like, well, I just have too many unknowns. I don't know what the time is. I'm looking for my displacement in the y direction. I don't know what my future velocity is. So that means I'm going to need to look at information on the left side of the equation, which means I'm going to need to solve for time. And so probably the easiest one would be this first equation, but you're going to notice that you're going to get basically what's called an identity, and it's not going to help you out in any case. So let's see if we can use this third equation to solve for time. So how about 34 is going to equal to half of 6.3 plus 6.3 times time. So this right side is the 6.3, and I'll have 34 divided by 6.3, which is about 5.3 seconds. So t is about 5.3 seconds, right? Which means I know all of this. And I know this number over here. So now I need to ask myself, do I have enough information to solve for y? And it doesn't look like it, right? I don't know what my v sub y piece is just yet. So this column right here still is holding me back. So let's figure that one out. Once I get that, I think I'll have all the pieces to solve on the right side for y. So keep in mind here that the value that I get for v sub y should be negative, because once I get right here, my velocity vector should be pointing downward. So at least that'll give me some clue if I at least have the right sign. And so I'm going to use the second equation in y to solve for, so I'm going to use these values here, it's 5.3 at the end, in case you can't see that, to solve for V final of y. So I'm going to use V final of y equals V naught of y plus ace of y times t. It's just a modified version of that second equation. It's right here. All right, so let's see what I get. So 9.8 times 5.3 is 51.94. If I take the difference between those two, I'm going to get negative 38.34. Remember, that's what I predicted, that it's at least negative because it's going down. So V sub y is equal to that number. All right, almost there. In this case, we were still looking for y, and now we have enough information because I know what V sub y is. I won't fill in the chart there. It's going to get too messy. So now I'm going to solve for y. Now I'll use the last equation here to solve for y. So I'm using a variation on that, which says that y is equal to V naught y times t plus 1/2 ace of y times t squared. Y is equal to, and remember, I should get some negative y value because my displacement went from some number up top here to something down below, which was negative. So it went in that direction. All right, let's see what I get. So V naught y was 13.6. T was about 5.3. Acceleration, negative 9.8. 5.3 squared. 5.3, square that. Multiply it by negative 4.9. Then add that to 13.6 times 5.3. And we get negative about 65.5 meters. Again, that was my indication that it was going down. Okay, so at least again, we have some understanding of if the sign is at least correct. Okay. So I'm not going to do number 15 for time purposes, but it's pretty much the same thing. Ball rolls over the edge of a platform with horizontal. This time it only has horizontal velocity, right? So that means that in the, let's see what I did here in my notes. That means it only has velocity in the x direction initially. So I just wrote down this as v because it didn't give me a specific number. It just told me that it was v. The height of the platform is 1.6 meters, and the horizontal range of the ball from the base is 20 meters. What is the magnitude of v? So you're looking for v. Keep in mind, because the object is following projectile motion, the initial and the final are both equal to v. So those are not check marks. Those are the letter v. The displacement is 20. The acceleration in the x direction is 0. We don't know the time. And then this should hopefully give you, based on what we just talked about, help you solve for that last problem. Okay, so that was number 15. All right, I'm going to go and start from the end here and try and work my way back up so that we can hit as many as we possibly can. Okay. And some of these we may not have gotten to this semester. We did not do angular momentum this semester. That was a repeat of number 2. But we did do torque. So let's look at number 57. Apologies for not having a problem in front. But essentially what this is saying is if we're given these 3 scenarios, or actually these 5 scenarios, which one of them is going to produce the most torque? All right. So we know that torque, the equation for torque was R perpendicular, that lever arm. This is the lever arm. And it's going to be perpendicular to the line of action of F. So there's our general formula. Right. And so we analyze each one of these 5 scenarios. So the first one just gives us that the torque is R times F. We have no clue in terms of what the R and F values are as of yet. If we look at the second one, and let me kind of back up a little bit, sorry. We have to pick a reference point. So our reference point is going to be here each time. And so what you're thinking is if I apply a force here in that direction, this object should rotate as such. Okay. And which one of those is going to give us the most torque or rotational force? And we're applying the same force, but at just different positions. If I applied halfway to this object, this might be, say, a door where it's attached at the hinge, we can see that the torque now becomes half of what it was over here. So this one now, in terms of comparison, has to be out. Number 3, if we look at the torque again, this is still the length of the object, but we always have to get to a point such that we're crossing the line of action of the force at a 90-degree angle. So here's the force, the line of action of the force. But we have to extend this out a little bit so we can kind of run into it at a 90-degree angle. So this force right here, this lever arm has to run into that force at a 90-degree angle. And so we extend the line of action of that force. And so the question now is, what is that arm lever length? You can kind of see it here. You can kind of see that this triangle is what we're looking at. Let's change that setting. Sorry, class. All right. Anyway, this triangle right here is what we're looking at. All right. It's filling in. I don't know why. I just don't want to take the time right now. All right. And then there is our angle, some angle, call it theta, as you can see right in here. So if we were to calculate R perpendicular, it would be R, the hypotenuse, times the cosine of theta. And so now we're here in terms of a comparison. And at this point, we don't know if this one or the first is greater or larger just yet. So we have to kind of pause on that. For number 4, same thing. Line of action. Extend the force line of action in this direction. Figure out R perpendicular. Right. So here's the torque. And so what I'm saying here at up above here is right here. I say that theta, the angle theta, is between 0 and 90 degrees. And as theta gets small, cosine of theta goes to 1. So what does that mean? That basically means that this thing right here is going to go to 1 as this value gets very large or gets very small, right? And so we pause right there. That still might be in the running, because I note right here that cosine of theta is at a max when theta is equal to 0. So we can see here that this thing is this angle theta, these angles right here are actually, this angle right here is not at 0. So it's not going to be at a max for us. And so finally, number 5, if we apply a force to the left, and just kind of think of this as sort of a door hinge, if you were simply to apply a force on the edge of that door, there would be no torque. It would not rotate in any kind of way. So the torque would be 0. Okay, so the final answer here is that this torque right here gives us the maximum torque given this force, right? And it overshadows this because, as I said over here, in order to maximize the torque, you want this angle right here to be at its greatest, and that would be at 90 degrees. Okay. All right. Sorry, that would be at yeah, it would be at 90 degrees, this angle right here. Okay. Let's look at number 58. Number 58 says that we have a guitar string and it's set into to vibrate at 512 hertz. We want to know how many oscillations does this undergo each minute. So we talked about frequency at the tail end here. And so frequency is equal to, one of the things we talked about was frequency was 1 over the period. And frequency was just another way of saying how many cycles, if a cycle constituted this, right, that one cycle over some given time, we want to know how many of those up and downs, if you will, are going to occur, how many of these things are going to occur per unit time. And our unit time is typically in seconds. Okay, so find the number of cycles or oscillations, but this time the question states in how many minutes. If you figure it out in seconds, easy to convert, right? Hertz is a matter of units or cycles per second. you'd have to do a conversion. So this implies 512 cycles per second. Convert that into minutes. That implies that it goes through about 30,000 cycles every minute. Okay. But just keep in mind, hertz are units of 1/time. So this conversion, the units here on the bottom would be something unitless up top. Or maybe you might want to think of that as a radian, if you will, per second. It's the same thing as a hertz. Okay. You're going to want to write down this moment of inertia chart for your index card. So make sure you have that. Okay. And then you don't need to worry about angular momentum. We didn't cover that. Let's look at number 52. Let me see if I can pull that problem up. Sorry, class. I might have to split the screen again. Just read it out to you guys. All right. All the way down to 52. You're not going to see it in the recording, so you're going to have to refer to the document. Thought I had them all printed out. And if you guys have any more questions, specific questions, we'll get those as well. All right, number 52, I'm gonna read it. So we're gonna have a figure, the triangle here, and it's gonna be a 60 centimeter length figure. So if we were to go all the way around the perimeter of this triangle, it is 60 centimeters. It's a uniform wire, which means that each one of these pieces in here are going to have the same, if you will, cross-sectional area. So it's pretty much homogeneous. It's going to be consistent in thickness, if you will. And we're going to bend it into this right triangle. And we're going to try and figure out what the coordinates, the X and Y coordinates of the center of mass or the center of gravity is for this triangle. Okay, so how do we start? The X center of mass in general, the formula is going to be the X component of the first mass times the X component of the first mass times its mass plus the X component of the second mass times its mass times the X component of the third mass times its mass. And then on the bottom, we're just going to sum up all the masses. That should probably be an M3 right there. All right, so what do you need to look at? You need to think of each one of the pieces here as a mass. All right, so let's look at this first piece right here. It told us that the length all the way around this triangle was 60 centimeters. And it also said that the total mass was 60 grams. And that was done for a reason. The reason why is if I were to take a cut out of this, let's just say a 1 centimeter cut, I would know how much mass I have in each one of the sides. So this side here is going to have a mass of 24 grams, right? It's going to be the same amount of grams as centimeters, just to make everything somewhat consistent. So this object over here, we treat as one mass, and it's going to have a mass of 10 grams. Likewise over here, this side is going to have a mass of 26 grams. And then we figure out where its center of mass, each one of their centers of masses are. So if I look at this first piece on the left side, we measure the center of mass right there in the middle. And its coordinates are at 0, 5. You can see that from my drawing. Right, so right there. The bottom piece down here, same thing. Its center of mass is at the halfway point at 12, 0, right in here. Now this last center of mass right here, you find by splitting up the triangle, and you take this triangle here, and you realize first off that, again, the center of mass of this piece here is going to be at the halfway point, but that doesn't help you in terms of the coordinates just yet. It's going to lie right there, 13 units or 13 centimeters down, but we need to know a little bit more. So there's that triangle over here. I'm drawing off to the right. It has a hypotenuse of 13. It has a leg of 12, which comes down here, and a height of 5. And when you do all that, it tells you that the center of mass for that 26 centimeter piece is going to be at 12, 5. Okay. So 3 pieces. We know their masses. We know the coordinates of their centers of masses. And now you're off and running. What I would suggest that you do is I would suggest that you open up a set of parentheses, as I've done right in here. Okay. So I usually open up a set of parentheses and then fill in the blanks after I've labeled everything. Right. So you might want to call this side over here M1. So therefore, this side, that X coordinate is going to be X1, and then the Y component is going to be Y1, so on and so forth. That'll keep you better organized. Okay. So you'll go through the entire process for both the X and Y, and you should come up with a center of mass at 10, 3, which it kind of makes sense. So it's going to be roughly 10 centimeters to the right, and then I think I said 3 centimeters, and then 3 centimeters up. So we got 10 there. So the center of mass is going to be roughly right in here. Okay. Okay, you guys have this on your test. I'm not going to go too much into this one. Let's see. This one actually is a little bit different. Let's read number 50. You guys had one similar to this. So we got an L-shaped object and it consists of three small masses that are connected. And connected by extremely light rods. So in this case, the rods have no mass. They're just connection points. And I asked for how much work is being done to accelerate this object. So to figure out how much work is going to be done, we use our work energy theorem, which says that the net work that's being done is the change in kinetic energy. This object has rotational kinetic energy. So it's kind of rotating about the x-axis. If you can visualize this in 3D, it's kind of rotating in that sense. Okay. And so that would be what it would look like about the x-axis, and about the y-axis, this thing would rotate, if you will. This goes back. Sorry, I'm not the, oh, here's a better drawing off to the right over here. So over here, you can kind of see about the x-axis, what it's doing, how it's rotating, and in the y direction, very similarly, it would be rotating as such. Okay, so just kind of think of this as a door, and the door kind of swings around out to the z-axis and swings around. Okay. I'll leave that one up there. Hopefully you guys can see that one. Let's look at number 49. We're almost done. Number 49 says that we have a figure of a person's foot. And in that figure, we have the Achilles tendon. And this is that Achilles tendon right here. It has a magnitude of force of 720 newtons. And we're trying to figure out what the magnitude of the torque that the force produces about the ankle joint. So we want to know how much rotational force this thing is applying. So, you know, how is it applied in that manner? So here's the picture, broken down picture of what you're looking at. And relative to the ankle, which is at A, we're looking for the torque. So in this case, remember I said, when we looked at torque, hopefully you can get to a problem in the next 10, 15 minutes where there's an equilibrium. But you typically want to determine a couple things. The reference point, which we've already figured out. And we want to know which way this thing is rotating relative to this reference point. So this force is going to have a tendency of wanting to rotate the foot and the ankle in that direction. And we know that when we rotate torques in a clockwise direction, this implies negative torque. When we rotate torques in a counterclockwise direction, this implies positive torque. Okay. Now for this one, it just asks for the magnitude, so we don't need to worry too much about if it's positive or negative. We're just trying to figure out how much torque, not the direction or how it relates to equilibrium. So once we get that, we're back down to our torque formula, R perpendicular times F. And R perpendicular is the one that we need to find. So one more time, relative to our reference point, we need to get to the force or the line of action of the force. And so we draw an R value. We draw an R value such that it runs into the force, that force vector, or if you had to, extend the line of action of the force out. In this case, we don't need to. We can see that we run into it at this 90-degree angle here. Off to the right, you can see this new form triangle. This length right here was given, or actually, let me see, let me think here. Just the angle is 50 degrees was given. The 3.5 centimeters. Trying to remember how that, I thought that was a given. Oh, yeah, it's given. So it's given down here, right? So there's that length right there. And here's that R perpendicular that we're looking for. We don't need to know this side over here. We have enough information to work with. And so when we solve for R perpendicular, we come up with that value of 0.0225 meters. We plug into that equation. Since we know the force is 720 newtons, we multiply that out. 720 times the 0.0225 is 16.2. So this, let's rewrite that. 16.2 meter. All right, number 48. I'm going to have to read that one to you because I don't have it. So we have this solid ball, and it has a mass of 1 kilogram, and it has a radius of 1 centimeter, and it's going to start from rest. We have everything here that are givens. It's going to roll down a 1 meter high ramp. So it's going to begin to roll in that manner. And it says that there's enough friction on the ramp to prevent the ball from slipping as it rolls down. Right. And so we're going to be at some point over here later on. And it's going to be rotating with some angular velocity of omega. So the question is, A, what is the forward speed that's a translational speed? And then B, what would the forward speed be of the ball if there were no friction? In other words, it would just slide. And part C, since the ball starts from the same height in both cases, why would the speed be different? Okay, so gonna go a little faster with this one. So with this one, if there were friction, we're going to assume that the ball rolls. And if the ball rolls, I'm going to have to kind of show you here each piece. We have our formula for our conservation of mechanical energy. This is got it kind of messy here, but all of this is our conservation of mechanical energy. And what does each one of these pieces mean? We have kinetic energy, K. We have gravitational potential energy here. And we have rotational kinetic energy. This first kinetic energy that I wrote is translational. That's just as it moves, straight down, down the ramp. And so initially, V naught was 0, so that's why I send that piece to 0, and it was not rolling. Okay, so you would start off with what I have in red there, and then you would clean it up, and you would get down to this piece right here. And then you should be able to solve for V. Okay, got cut off a little bit. And then the second time around, I didn't do it, but the second time around, what you would have to do is you would start off with the same formula that I have up here. See if I can try and grab as much of this as I can. God dog it. Sorry. So you're going to look at what I have in red right here, and then understand that there's no rotation in this case. What you have is you have a ball. See if I can just kind of, it's almost like what we started off doing earlier in the semester. We just have a ball just sliding down with no rotation. Okay. And so what that would mean is that there would be no omega final, because there's no rotation, there's no spinning. Everything else should be the same. Okay. So you want to look at that from that perspective as well. All right. So I'm going to go slowly through these. I'm going to try and work my way back so you have them for the recording. If you see anything that you want me to look at in the next 5 minutes, we can. There's an impulse problem. Here's conservation of momentum. Here's another conservation of momentum with impulse in it. Here's a block on an inclined plane. You definitely are going to need to know the forces that are active or operate.
Hello. It's currently 4:40 p.m.
You're going to want to know all the forces that are acting on this object, right? So you, let's see, I'm trying to relate this to that last problem with the ball rolling down the hill that was sliding and then and rotating. So you can probably put some work into using this as well. So make sure you get how I have all of these forces that are acting on this object here. Everybody should be familiar with the normal force. You should understand that the weight component is this vector right here. It always goes down to the bottom edge of your paper. But in terms of helping us do the math, we had to decompose that weight vector into vector in the x direction, which we, in this case, determined to be down the ramp. And then the weight component in the y direction, which is as such. And it knocked out this vector here. So when you get motion in such a manner up and down the ramp, you're going to have to tilt the XY axis. All right. Otherwise, if you use a standard XY axis, you won't be able to add any of the vectors, especially that normal force, because the normal force is always perpendicular to the surface of contact. Okay. So this is just a repeat there. 32. This is just a problem we had on the test. We had a block moving up a surface. So I'll let you go through that one. It just asks how much work does that force do on the object? And our work formula is work is equal to force times displacement times cosine of the angle in between the angle and displacement. It's just old stuff there. 29, you should know the universal law of gravitation, big F of G. Here again is just an object that is on an incline. I can't remember. Oh, I was going to say, is this thing moving or not? This thing has to be moving because there's kinetic friction involved here. I'll start up here so you guys can see it from top down. I solved it. So that was 27. 26. This time it was on same type of problem, except it was on a horizontal surface. And I was looking for the maximum amount of static friction that can be imposed such that the block does not move. And those are the majority of the problems. Okay. So, as I said before, your test is going to be on Tuesday. Go all the way up to where I started. So Tuesday, July 23rd, I'll try and send out an email just to kind of remind you. Just FYI, it's going to be kind of hard next week for me to respond back to emails. If it's of the urgent kind, you might want to kind of give me a call because I'm working on getting grades put together. That way I know it's urgent. Let's go right. Remember my number. I think it's 727-791-2503. It's my office. Okay. In terms of your final grades are going to be in my SPC, not my courses. What do I mean about that? By that, your my courses grades are unofficial. So what's going to happen is I'm going to be working on things. I'm going to be trying to get everything up to speed. You may see some things where maybe I'll, and sometimes I have to shut down the site for a second so I can move some things around. But you need to check in my SPC, and I'll have all those in the system by Friday at 4 o'clock. All right. So I cannot tell you at this point or anytime next week what your grade is. You're going to have to look inside the MySPC. If you think I've made a mistake, maybe there's an error or some kind, call me. All right. It's not gonna be an urgent matter at that point. You can call me. If you feel like it's gonna be urgent, feel free to call me. But if you think there's an error, we can always get it rectified the following week. We can always do a grade change. Okay. But I would think I would hope that by now you've been kind of tracking where you are with your grades. You have a pretty good idea of where you stand. You know that 70% of your grade, I believe 70, comes from your tests. 15 comes from homework, and the other 15 comes from the final exam. We drop one of the tests. Sometimes in my courses, the calculations don't go right. So that's why everybody should be able to figure that number out. I think I put in manually everybody's homework score. So out of 85, you should have a pretty good idea of where you stand. But I'll be working on those really hard over the weekend and into next week. So that's why, if you ask me, if you send me an email, I'm probably not gonna get back to you because I'm gonna be working really hard and I kind of shut things down so I can get all these classes taken care of. Okay. So just be mindful of that. Just call me, but it needs to be of the urgent matter. Okay. All right. Any questions up to this point? Anything that I may have missed out or forgotten?
I just had one question about the grade.
Sure.
So
Sure.
since the final grade's obviously not in there yet, would you
Right.
say that the grade that we're seeing in my courses right now is the lowest possible grade that we could get?
The lowest possible grade.
Since because it's weighted out of 100, so it's adding up all of like the weighted points. And we haven't taken the final yet. I was just curious because I'm trying to get an idea of like what I need on the final to get the
Oh,
grade that I want.
I can. If you send me an email, I can. I can put. I can put something together for you. I can tell you.
Okay. All right.
Yeah.
Thank you.
You're welcome. Anything else? All right. That's my time. I went over a few minutes, but I thought it was important that we go through that. Drive safe if you're driving home. Take care.